Okay, we're going to take a look at some exponential applications. The first application we're going to look at here is exponential growth or decay. And so exponential functions are used to model situations where the dependent variable, remember that is your y, changes. It increases or decreases by a constant factor for each 1 unit change in the independent. Remember that's x. So notice how these are changing by 1. And here is your dependent variable salary. Upon graduating from college, Ashley took a job with a starting salary of $40,000. Here it is. She can expect a 6% raise in pay each year, computer salary for the first 4 years. Okay, so doing this by hand, we would take 40,000 times the percent raise. Make sure you change your percent to a decimal. So first thing you want to do here is change 6% to decimal, which would be to divide by 100. So our decimal, it would be 0.06. So taking 40,000 times our 6%, and I missed a 0 in there. Press enter. So she increased her salary after 1 year by $2,400. So it increased by $2,400. So her salary for the second year is $42,400. Okay? So again, we're going to take $42,400 times 6%, and we're going to add that to $42,400. So multiplying this by 6%, we get $2,544 salary increase, which now puts her at $44,940. Okay, so I finished filling out the table. That was $44,944, by the way. And then I multiplied that by the 6%. So this shows her increase in salary, added it on, new salary. Okay? So it says write a function for Ashley's salary after 2 years. So first of all, you know that we're dealing with an exponential function here. So our independent variable in this case is going to be t, and a of t is going to represent Ashley's salary in terms of t. So her initial amount, the amount that she's going to start off with, is 40,000. That's going to represent your a value. Now, in order to find the base is going to represent the rate, okay, of increase or the rate of decrease. So in this case, her salary is increasing. So to find the rate, we would take 1 for 100% plus the rate, which is 6%. So the base for this function is going to be 1.06. 1 for 100%. She's going to get 100% of her salary, and she's going to get 6% of her salary. And it's going to be in t years. So this is going to represent Ashley's function in terms of time. Ashley's salary in terms of time. Okay, so it says graph the function for 0 to 30 years. So obviously time is going to go down here, starting off with 0. I'm going to go ahead and go by 5s. You could go by ones. Now, for my Y scale, that's going to represent my salary. This is time, and it's in years. That's my units. This is going to represent salary. Ashley's salary, A of T. And this is going to be in dollars. Okay, so she's starting off at 40,000. But in 30 years, where does she end up? Well, let's find out really quick here. We'll use the function that we wrote. So we have $40,000 that she started off with, her initial amount, times her rate. It's an increase. It's greater than 1, so it's an increasing function. And we'll raise that to 30 years. And let's see how much money. Ooh, $229,740. Now, I would like a job like that. That is quite a nice pay after 30 years of work. Wow, I wish my salary was like that. So we're going to go from 40,000 all the way to 230,000. So let's see. I think I'm going to go ahead and go by 50,000. 50K. Remember, K means 1,000. And so we're going to go ahead and plot this. We know that at the initial value of Ashley's salary was about 40,000. After 5 years, let's see if I go up, over, no, up, I'm not sure, enter, there we go, and I want 5 years. So $53,529. That's about right. Okay, and then what I'm doing here is I'm going up, I'm highlighting, arrowing over, I'm highlighting what it is that I want to recalculate. I'm pressing enter, and then I am arrowing over and I'm changing the number. This would be for 10 years. 71,000, a little over $71,000. So somewhere in here. $71,000 somewhere in here. And calculating the rest of this. And I'm going to draw my line through those points. Or I should say my function, because it's not a line, it's a curve. And you should recognize this as a growth, an exponential growth, with an initial starting value of 40,000. That's always going to be your A value. Okay? So I'll let you fill those 3 pieces in. See if you can figure those out. I'll check those off when I check your video notes tomorrow. Turn the page. Here is some information for an exponential growth or decay model. Notice that A of T is amount at time T. Okay, so this is the amount, like Ashley's salary at time 0, which would be $40,000, and so on. A sub 0, 0 representing the initial amount, so this is going to be 40,000, the initial amount. How much do we start with? Starting amount. Okay, B, we kind of did this before. Since it was a growth, we did 1 plus R. We did 1 plus the 0.06 for our growth. And if it's a decay, we would do 1 minus R if it was a decay. And R is your rate of change. T is going to obviously be your time. Let's take a look at number 2. If you drank one soft drink, the formula for the amount of caffeine in milligrams left in your body after 10 hours would be as follows. What is the initial amount? That's going to be, what do you think? That's correct, Stephanie. 100. The initial amount is your A value. What is the rate of change as a percentage? Don't put 86%. Do not. Okay? Remember, we want the rate. So we need to calculate what R is. What is the rate? Now, did we add to 1 or did we subtract from 1 to get 0.86? If you said subtract, Demetrius, you're correct. You would subtract. How much would you subtract from 1 to get 0.86? 14. 1 minus 0.14 equals 0.86. Good job, Andreas. So 0.14 is our decimal. We want to write it as a percent. So remember, to write a decimal as a percent, you multiply it by 100. So we're going to have 14%. That's our rate of change. How much caffeine is in the body after 5 hours? We just plug 5 in for T. And you're going to get your answer. So 100, parentheses, we have 0.86, a decay, arrow out, caret, 5 hours, we have 47.0427 milligrams of caffeine. Okay? It says, when will the amount of caffeine in the body be less than 10 milligrams? At this point, one of the things you could do is you could just keep plugging in numbers for T until you get below 10. So at this point, you could go to your graph, plug in your function, use X for T, okay, go to your table, Control T, oops, gotta graph it first, graph it. It's okay if nothing shows up. Go ahead and press Control T, alright, and so notice here we have at 0, when time is 0, we have 100 milligrams of caffeine, and as time increases, the amount of caffeine decreases. And so at some point, Mr. Kramer would need to go get a Mountain Dew to increase that caffeine level so he can make it through the day. Yes, Mountain Dew is awesome. So notice at 15, and we're talking about hours here, at 15 hours, we're still above 10. So it looks like at 16 hours, we have less than 10 milligrams. 16 hours. Okay, and so I'm going to let you answer this one. Let's take a look at the next one. And time is running out, so we will start here with part 2 next time. See you guys in class tomorrow.